morning, Chem 1. Today is day 2 of Unit 12. We found out recently that we will be doing remote learning for the rest of the school year. I know that probably leaves you with a lot of questions. I have a lot of questions. Um, those answers I'm sure will be rolling out here in the next few weeks. But our job is just to kind of stay the course and keep doing what we're doing. Um, couple things just update wise. I've started to put Z's in for your grades, and that's simply because I have a lot of outstanding assignments, and I think it's because people don't realize, like, hey, you're missing this because it's not showing up on your grade. So that doesn't mean that it's a Z forever. It just is my way of telling you, hey, this is missing. I need this from you. All right, and you can email me or contact me about anything, but I hope that's what we did during class, and I think it's just a better way to remind you that you have things that are outstanding. The other thing is you can retake quizzes. I've had people starting to do that. They email me, they say which quiz they want to retake, and I go in and fix it. And so please make sure you take advantage of that. And that's all I really got. Okay, this has been a fun week for me. I got a new camera for my birthday, and we've been doing some slow-mo footage. So we got some slow-mo footage of some birds taking off, and I got some slow-mo footage of my kids. We made a little highlight video. It was pretty cool. It was pretty cool. It was a lot of fun. Yeah, that's all I really know about that. But one of those slow-mo footage things was bubbles, which is a liquid. See, it's a perfect tie-in. It's the same thing, really. I mean, it gives me a chance to just talk about nothingness for a few seconds before these videos, you know. And also, but yeah. So anyway, today we're gonna talk about liquids. I will say something about this unit, this section. I don't believe there's any math. There's no math. States of matter, Unit 12, is pretty much all conceptual stuff and understanding the properties of liquids and understanding the properties of solids. We did Unit 11 by itself as gas laws, lots of math. But Unit 12 is more like properties of those liquids and solids and how they go along with that. And in order to talk about solids and liquids, we're going to go back to the kinetic molecular theory. You remember with the kinetic molecular theory, with gases, we said particles are always moving. Their average kinetic energy is manifested by temperature, okay? And that's how they're moving randomly, okay? Liquids and solids are going to have stronger intermolecular forces. So think like dipole-dipole forces, okay? And that's going to pull them together in a way that makes them liquid or solid. They're very rarely gases. Most gases, if you think, are diatomic, which is going to make them nonpolar, and so they're only going to have LDFs, like O2, N2, F2. Like, those are all gases. Why? Because they have weak intermolecular forces. All right? So today we're literally just going to take a look at liquids, and we're just going to talk about properties of liquids. The first thing you probably learned in like 3rd, 4th grade, which is liquids have a definite volume, okay, which means we can measure its volume, but an indefinite shape, and it has one free surface on the top. Doesn't matter what container you put it in, it's going to take the shape of that container. Typically speaking, liquids are going to be more dense than their gases and less dense than solids. Now we know that this isn't always the case because we know that actually the least dense phase of water is actually, well, it's gas, but then the next least dense would be the solid. And that's why ice floats on top of the liquid of water, okay? So it usually goes least dense gas, most dense solid, but there are substances where that gets flipped around depending on how that solid crystallizes. Liquids can't be compressed. Gas laws are based on the idea that we can add pressure to a gas and change the volume, right? That's Boyle's law. But that does not happen with liquids or solids, okay? You can't just compress a liquid. They have definite volumes. Fluidity is the ability to flow, okay? Liquids and gases are technically both considered fluids, okay? Typically, when I say fluid, you think of a liquid, but gases actually behave in a fluid with fluid-like properties. Liquids are less fluid than gases because the stronger intermolecular forces don't allow those molecules to slide past one another. okay, because liquids have stronger intermolecular forces. The weaker the inner attractive forces, the more fluid the liquid would be, okay? So you can start to think maybe a little bit about liquids with strong intermolecular forces or liquids with weak intermolecular forces based on how well it flows, okay? Which brings us to viscosity. So you have fluidity, how well does it flow? And then we have viscosity, how much does it resist flowing? And the intermolecular force part is key here, okay? The stronger the intermolecular forces, the more resistant to flow it would be. So if you look at the examples here, we have honey, syrup, molasses, okay? Those substances resist flow. They're not very fluid, and it's because they have really strong intermolecular forces holding those molecules together, and they don't want to slide past one another, okay? Something like water flows very well, has a very low viscosity, it does not resist flowing, okay? And you think, well, water has hydrogen bonding. There's other things going on besides the intermolecular forces, but the intermolecular force trend is really what we want you to know. Understand that stronger, more resistant to flow, weaker, less resistant to flow. We can affect viscosity with temperature. Okay, if we speed these molecules up by adding heat, they're going to more likely slide past one another. A good example of this is like when you have that honey and that bear and you want it to like flow better, you put it in the microwave or you put it in a boiling water, and it helps like reliquefy the honey, okay, or make it less viscous. All right, just a little chart. You can see how water has really low viscosity, and heavy syrup like corn syrup would have a high viscosity, a high resistance to flow, okay? And it's because it's trying to show down here that that's because of how the bonds are, okay, in between those molecules. Not bonds, intermolecular forces, okay? Volatility, okay? Once again, we're going to revolve around the idea of intermolecular forces here. Volatility is how easily a liquid evaporates. So you can already think in your mind, water takes a little while to evaporate. Think of things that evaporate real quickly. Alcohol, gasoline. You know how you know gasoline evaporates quickly is because, I mean, you might see it if you spill some when you're putting it in your car, but also because you smell it so quickly. Typically things have a real strong odor, they're evaporating like really fast, okay? And so we'd say they have a high volatility. So if things evaporate really fast, that means molecules are willing to separate, which means they would have weak intermolecular forces. Things with strong intermolecular forces do not evaporate easy. So you could think like, we just said honey has a strong intermolecular force, correct? Well, does honey evaporate very easily? No, it doesn't. Okay, you could sit it on your counter and it might dry out and some of the water might come out of it, but for the most part, it's not going to evaporate very easily. It's because of those strong intermolecular forces. So the weaker the attractive force, the weaker the intermolecular forces, the more volatile it'll be, the more it'll evaporate. Okay, you'll do a lab experiment based on that here coming up maybe next week. Okay. The volatility of a substance kind of gets into vapor pressure. Vapor pressure is it's the pressure from the vapor, ooh, that's fancy, over the surface of the liquid. So if you have a glass of open water, the water molecules are pushing up against the atmosphere, okay? And we call that the vapor pressure. It's the force at which those molecules are trying to escape from the liquid to the gas phase, okay? And once again, it should make logical sense, if something has really strong intermolecular forces, it's going to have very low vapor pressure because it's going to want to stay together. If it has weak intermolecular forces, those liquid particles are going to become gas, and therefore it's going to have a high vapor pressure, okay? Does that make sense? And this affects boiling point. I know a lot of times we associate boiling point with heat, okay? But boiling point is basically the ability of that liquid to overcome the atmospheric pressure. The vapor pressure needs to overcome the atmospheric pressure, okay? That upward push has got to be greater than the downward push of the atmosphere. So the higher the attractive forces, the more that liquid wants to stay together, the higher the boiling point. That makes sense. The more heat we're going to have to add to get it to boil, okay? If those molecules are attracted to one another. Surface tension. We know some things. We know water has strong surface tension, and that's because it has strong intermolecular forces, meaning those molecules of water want to stay together, okay? It says the skin-like nature of liquids. Okay, water's a good example of this. A better example of this would be mercury. Mercury, a liquid, has very, very strong intermolecular forces. And so because of that, if you put mercury and let's say acetone, and this is glass or water on a surface, they're going to bubble up based on their surface tension. Mercury almost bubbles up into a complete sphere because its intermolecular forces are so strong and so attracted to each other that it literally just does not interact with the environment. Water is a little less strong, okay, but it'll still bubble up like that. Something like acetone, which has weak intermolecular forces, almost lays flat because there's no intermolecular forces pulling it toward itself, and it'll just lay on whatever surface it is. Surface tension can be disrupted with something called a surfactant. This is something that kind of gets in the way of those intermolecular bonds and disrupts the surface tension. Soaps, detergents are surfactants. Okay, remember that you'll need that for the lab. Remember the word surfactant. Okay, you'll see it again. And the last one here is capillary action, and once again, intermolecular forces are what it's based on. Adhesion is the force of attraction between non-similar particles, and then cohesion is between similar particles. So if we think about like water and a capillary tube, the water's attraction for itself is cohesion, but then the water also has attraction for the side of the tube, the glass. That's adhesion. Capillary action occurs when the adhesive forces, so the forces attracted to this side of this glass tube, would be greater than it has attraction to itself. So because of this, what's going to happen is this water is going to kind of crawl up the sides, and it's going to give us what we call a meniscus. Okay? If it's opposite, like we said, mercury has great strong intermolecular forces. Because of that, mercury creates like an inverted meniscus because it's attracted to itself, intermolecular forces, more than it's attracted to the glass tube. Typically speaking, the more narrow the tube, the higher the fluid is going to climb up. Okay? Capillary action is a lot of times it's discussed. There's a lot of different experiments you can do here, but a lot of times it's discussed with plants, which kind of comes into play, but there's something different going on there too. But it's the same idea, really thin tubes carrying water upward. So that's really the PowerPoint, okay? There's an activity, which is a chart that just kind of has you walk through all these properties. It would be a good thing to go through and a good question to answer. You're probably going to see some stuff on the quiz Friday from this PowerPoint. I believe that these quizzes for this section are going to be easier because it's all content, and you should theoretically have that content right in front of you. Like, there's no math to figure out. It's just, are you willing to take the time to understand the PowerPoints and things like that, and then go apply that to a quiz that's going to be pretty straightforward and direct. But this stuff kind of takes a little while to wrap your head around. I will say this. All of those properties we went over, it all comes back to those intermolecular forces we talked about in 12.1. If intermolecular forces are strong, it's going to like create all these other situations. Higher boiling point, lower vapor pressure, higher viscosity, okay, lower fluidity. Like you should be, if I say strong intermolecular forces, you should be able to walk down the properties that we just went through and say this is how that property is going to behave based on strong intermolecular forces, and vice versa if they're weak intermolecular forces. That's the name of the game. Okay, that's what we're kind of doing here, is just taking liquid properties and applying them to intermolecular forces that we talked about at the beginning of this semester. Okay, so keep at it. The activity today, some people have been asking about, like, how would I turn in the activities? I'm not having you turn in the activities. Okay, I'm finding out if you did the activity based on like the quizzes on the end of the week because I'm putting the activity information in those quizzes. Okay, so the idea is if you do the activity, it should make those quizzes on Friday pretty simple. Okay, that's the plan. Um, Good job today. Keep up the good work. Let me know if you have questions. Be good to somebody today. We will see you